Manchester's not quite sure about it. I'll explain about that.
Hi. Yeah, to clarify so I forgot to ask in advance, should I be speaking into the mic or are we not using those?
The mic is on, but
Okay, it sounds about the same.
speak loud enough then.
Okay, whatever. Yes, to clarify the title slide, this is all about my PhD work that I did whilst I was at the University of Cambridge. I was a systems person at the University of Cambridge rather than a programming languages specialist, and I sort of stumbled sideways into programming languages, so any ignorance that's caused by that, apologies in advance. I am currently affiliated with the University of Manchester, but I'm not a researcher there. I'm working with some biologists with Cancer Research UK Manchester in an attempt to sort of harvest some low-hanging fruit regarding how to do their analyses. So that doesn't really have anything to do with the LLVM stuff. That's all relating to the Cambridge stuff that's in the past. But that would have been a bit of a long title slide, so I thought I'd just say that. Okay, so today I'm going to talk about LLPE. LLPE is a partial evaluator / program specializer that targets LLVM intermediate representation, making it effectively a cross-module partial evaluator for C, C++, Fortran, yada yada yada, whatever you can lower to LLVM IR without all your instructions being tagged with memory ordering tags, i.e. Java. We support like 99% or so of LLVM IR. We can do sort of things that stumble your classical C partial evaluators, which are typically sort of implementation-defined things that are depending on exactly how your C code has turned out to manifest in terms of memory and memory layout and things like that. And we can handle multi-threaded programs that interact with the kernel. Like I say, I was working with the systems group. The point of all this was to try to bring specialization to bear on big programs, real programs, practical programs. But we'll get to the practical experiences. First, we'll talk a bit about the actual evaluator. So here's the rough sort of running order. For anybody that's not particularly familiar with partial evaluation, then we'll just give a very quick overview of what we're talking about. Talk about a bit about LLPE and what it can do and what it can't do. Talk about the practical experience that I had in the course of doing this as my thesis project, what kind of things I was able to specialize and what kind of benefits I got from that. A brief review of LLVM as a working environment for this sort of project. Would I do it again? Would I recommend that you do it? And the current status of the project. It's sort of just getting on its feet as sort of a proper project as opposed to just academic code, and sort of come and check it out and play with it and have fun with it. Okay, so let's start with the brief PE review. Anybody that is a partial evaluation expert, take a 3-minute nap starting now. Okay. So the first attempts at partial evaluation were all about functional languages. They were typically expressed against Lisp or Scheme, one of the languages of that ilk. And it was all about taking functions and then taking some things we think we know about how they're going to be used. Typically, in the case of functional languages, that would be the value of some direct parameter, and producing specialized variants of functions according to that. So here we've got a really, really simple case of a function which takes 2 parameters and a specialized variant that knows the value of x but not the value of y. That's basically all we're doing. So in the case of imperative code, it looks a little bit funkier and there's typically more characters, but otherwise we're doing similar things. We're taking things like this little function which just takes a byte-wise XOR of a string to make a checksum or something. Feeding in some known value. So here we don't know what the initial value is that we're folding into the checksum, but we do know what the string is, and unspooling this loop and turning that into much simplified, much shrunk code which has the same meaning, assuming that the parameter was supplied as expected. The tricky bit, of course, comes when there's things we don't know about how the program is going to run. because we don't have all the information available. We only know some of our parameters. Some of our parameters remain unspecialized. So here we've got a digest function which can be told what it's going to digest and what algorithm it's going to use to do the digest. And if I tell it that I'm going to digest the string LLPE, but I'm not telling you which algorithm to do it, then should I go and specialize each one of the sub-calls within that? Because obviously we don't know which way this if branch at the outside is actually going to go, but we do know what the data is that's going to be passed into the individual digest functions. So should I go into each one of those and specialize them in context, or should I say there's too big a risk of like code blow up? I'm going to hold fire on that and keep the code as it was. So basically, what we're going to end up doing is like inlining a lot of functions. We're going to end up peeling a lot of loop iterations in order to try to extract opportunities for essentially really aggressive constant propagation, really aggressive linearization of control flow whenever the opportunity presents itself. And we're particularly going to have this problem of what do we do whenever control flow is uncertain during specialization. Do we specialize both or many of the possible paths that the program should go down? Should we stop specializing whenever we see uncertainty of that kind? Should we take hints from the user? Should we use some heuristics to figure it out? Okay, so LLPE, the actual thing that exists rather than the just the theory. So all the real gains that we're making are due to the really, really basic things. Like the actual savings in time and space just boil down to taking direct arithmetic instructions and reducing those to constants, and taking branches where we've been able to figure out where they're going to go and turning those into unconditional branches. And everything else we've got is about making those things possible in a much more aggressive way than just conventional constant folding that we see in the ordinary optimization passes. So the first big thing we're going to need to deal with is this uncertain control flow problem. We got this situation that we got some test and we don't know which way it's actually going to go, and then we got this phi node at the bottom which could take two different values depending on which way we went, and during specialization we don't know which way we've gone. And the approach that LLPE takes to this is that we will assign a set value to the phi node at the bottom here, representing the fact that it can take one of two possible values rather than just being unknown. So we're going to be running over this program and assigning things which are sort of higher typed than basic LLVM IR. We will be representing this kind of thing which can't be represented directly in IR, but where we know a little bit more than just that it's either unknown or a constant. The purpose of that, of course, is that later in the program we might come and look at this phi node and say switch on it, and using the information that it's either one or two, but we don't know which one, we could eliminate some of those switch paths. The second big thing we're going to need to deal with is what to do when we encounter calls and loops during a function that we're trying to specialize. In the case of non-recursive function calls, LLPE's strategy is that we always descend into those calls interpreter fashion. So that makes it essentially maximally context sensitive. And that's where a lot of the gains we're getting come over just ordinary constant propagation, is the fact that we're going to try and investigate things in context as much as we can. Of course, that's going to have some big performance impacts, and we'll come to how we're dealing with those later on. Whenever we enter a potentially unbounded loop or recursive call, we have a problem there. We need to figure out whether we should descend into that or whether we should try to do some summary analysis. And the strategy used at the moment is that if, considering the circumstances we're specializing according to, we are certain to get there, then we will do unbounded descent into that loop or call. If we are not certain to descend in it, then there is a risk that we will do infinite specialization if we attempt to just keep on descending and descending and descending. And therefore, at that point, we would take a fixed point solution over either the loop or the mutually recursive functions that are presenting us with that obstacle. Next up, how's LLP handling memory operations? Well, we got three kinds of things in LLVM that generate symbolic memory objects. They, of course, stack allocations, heap allocations, where at the moment it's just hardwired to consider the standard C allocator, but you can, of course, strap in whatever allocator you care to use, and globals. And all of those things are represented within LLP as symbolic pointers. So those are pointers to objects which we know or expect to exist at runtime, but we don't actually know the values of the pointers. So we're not actually executing the allocator. We don't know the actual memory layout at this point, but we do know that they're symbolic objects. It's fine within specialization to cast those symbolic pointers to integer types and back, and you can do pointer arithmetic and comparison on them. The one thing we can't answer is what the actual bytes are of the pointer, and we also can't answer less than comparisons relating pointers to different objects. Those do present us with a few obstacles. Those do present us with some programs that we can't specialize effectively. Typically that's because they use pointers within ordered maps, for example, which of course do less than comparisons on them, and those have to be manually handled. And the other one is, of course, putting pointers in things like hash tables, where again we care about the specific bytes in order to figure out what hash bucket the pointer is going to go into. And that presents us with an obstacle. That means that, again, that's something we need to annotate if we're going to effectively specialize that kind of code. So these symbolic pointers that we're passing around within our specializer, loads from those symbolic pointers can often be actually resolved during specialization in order to eliminate memory operations during the specialization phase, and thus get those out of the way now, and so they're not in the specialized program at all. And stores that write to symbolic memory can be proven to be unnecessary in the specialized program whenever we manage to eliminate all readers from them. So as we proceed through the program, stores are being killed off as we go, whenever we find that the load was able to be resolved to a constant, and therefore the store load pair, or the several stores and several loads, are now eligible to be eliminated. This is much more aggressive than LLVM's basic dead store elimination. Symbolic memory is also being forked and merged. So we talked a little bit earlier about phi nodes that contain several values. That was this one. That was where we had uncertain control flow, and we had a phi node where the specializer was going to say about the phi node, this is either 1 or 2, but we're not sure which one. And in the case of memory, the entire symbolic memory is being forked whenever control flow diverges, and is being merged whenever it converges, using some fun copy-on-write data structures in order to make that not colossally expensive. So that means that your whole memory in the context of this specializer can contain set-typed values. So memory locations can have several possible constant values, several possible symbolic pointers, and things of that ilk. And the purpose of doing all that is basically just to try to constrain as tightly as we can, especially pointers. So throughout this whole enterprise, one of our main goals really is to know in your entire symbolic memory where do all your pointers lead to, just to try and restrict as much as possible the thing that stumbles us really badly, which is whenever there's a write to memory where we just don't know where it goes. So that's why we're pursuing this kind of option. Next up on the hit list, we got some support for I/O in here. So much as allocation instructions during specialization are generating symbolic pointers that we're passing around the program, calls to, so here just open, it's currently hard-baked to use the Linux system call API, but of course that can be changed. But calls to open where we know what you're actually opening, and we know that you're opening it to read, turn into symbolic file descriptors. And then those can be stored in symbolic memory and passed around and what have you. And then those can end up in read calls and seek calls and things like that. and can be manipulated in the obvious way during specialization. And the purpose of this is that your program actually during the specialization phase can consume information from files, and then the specialized program, rather than actually reading and computing on that data in full, can just do a quick check that the file is in the same state as it was during specialization, rather than having to do a full reread. And that was the focus of the as a practical use of the system, so I'll talk in a bit more detail about that later. As with anything in LLPE that might fail, this entails duplicating some code to take care of the case where your expectation turns out to be false. So here the potential failure case is, of course, that I ran my specializer, it read data from a file, then you modified the file, then you ran the specialized program. Of course, that's going to go wrong if we don't make some checks to ensure that the file actually is as we expect it to be. And in that case, we're going to duplicate code which is downstream of that particular block and retain an unmodified version of any code which is reachable from there that we can branch into whenever that turns out to be false. So we're just bailing out of our specialization at that point and returning to the vanilla program, if you like. Next, threads and processes need to be dealt with. Of course, this gets a little bit tricky to do good specializations whenever we have potential concurrent action by other threads, by other processes. And we're going to recognize, and also by signal handlers, of course, which could just interrupt us at any given moment. LLVM's a really lovely environment in which to be working on this, because it does give us a clear indication of when it's necessary to yield to another thread. So this is just any instruction which is annotated volatile, implying that we must admit outside action having taken effect just now. And anything which has the memory ordering attributes that were talked about at the beginning of the day, any of those which indicate that we must admit the possibility of outside action between then and now, that is a trigger that we're vulnerable to concurrent action messing up our specialization. So what we're going to do is whenever we pass this point where we needed to allow outside threads to run or to have run, we're going to tag our symbolic memory, and we're going to tag the entire memory tentative. So what I mean by that is I'm pretty certain that it has particular values, but they might have been modified by the other thread, by the other process, whatever. What happens then is whenever you load from symbolic memory, and we think we know it, but it's tentative, that means it's time for a runtime check. That means we need to check that the value is actually as expected. Much like in the case where a file had been modified by concurrent action by another process, by the user, whatever, in that case we're going to bail out of our specialization and branch into unmodified code in the same way. If the pass checks, however, if the check passes, however, we can then tag the memory non-tentative concrete again, and that means that we don't need to check that particular location again until such time as there is further concurrent action. Now, as you might expect, that means that if we have a process where concurrency tagged instructions are frequent, then the results will be very bad, because practically every access will have to be checked. We'll spend all of our time checking and practically none of our time actually saving time because we've got rid of work using specialization. The kind of case where this is useful is where you have, typically you've got a synchronization point and then you've got a big block of work which is done thread locally, and therefore which is suitable for us to specialize, but we do have to check that the synchronization point didn't do anything unexpected. And then we resynchronize afterwards. So you do need your blocks in between the synchronization points to be pretty large in order for these checks not to become prohibitive, both in terms of code size and in terms of the time cost of making them. Okay, so that's the sort of the end of the laundry list, the sort of overview of things we can deal with and roughly how we deal with them. Obviously, I'm aware there's a lot of detail missing there. It would take a long time to read it all out, but there'll be some pointers at the end to sort of where is the complete documentation. So limitations. So we got pretty broad support for LLVM IR, but there are a few missing pieces. One of the big pieces we're missing is we can't specialize any program where a throw and catch is part of the path that we want to specialize. So it's perfectly acceptable for exceptions to be there, and it's acceptable for exceptions still to be there in the specialized program. The case we couldn't specialize constructively is if throw and catch is part of the normal flow. Like that's part of the path that we actually want to specialize along. So a good example of that would be, obviously it's not often targeted to LLVM, but like Python iterators. The normal way for a Python iterator to finish is by throwing. And so if that pattern existed in your language, then you wouldn't be able to specialize any of your loops because the exit path would be unfathomable to the specializer. The reason for that is that the throw and propagate process, certainly in the exception implementation that I'm used to, has been introspecting on the binary in order to go read some dwarf information in order to direct the exception propagation process. We can't do that because we don't have the binary just yet, and therefore exception propagation is off limits just at the moment. I'm sure some fun tricks could be done, but I can't quite see how they're going to be done right now. And thankfully, because we're working in C++ and because C++ exceptions are so deeply unfashionable, we've been able to get away without having to do too much work on that right now. The next big limitation we got is threads, as implied by all that talk about tentative memory and checking that your memory has not been modified by concurrent action by another thread. We can only really specialize when the essence of the program is that it is single-threaded with occasional risks of concurrent action, but the concurrent action is unexpected. If the concurrent action is part of the expected path, we're not going to be able to do anything too useful for you right now. I do have some neat ideas for how that might work. I'm sure they're horribly flawed and that I would find that out in the course of like a further 3 years of research. I'm not going to do that right now, but that is a current limitation. So for example, if you have some thread which is doing work and it's just occasionally checking for a flag that would shoot it down prematurely, that's fine. That's going to work really well because the shoot down flag is just going to introduce some checks. The expected path is that we don't get shot down. A case that would work really badly is if we had, say, a producer-consumer kind of situation where we got two threads generating work and consuming work, and to meaningfully get work done at specialization time, I need to model that relationship between those two threads. That's not a thing we're targeting right now. That's not going to specialize well right now, but future work, big future work. And then, of course, the other big limitation is when we hit big, horrible assembly sections that could do anything. All bets are off. Those are thankfully rare, as I've been doing it so far, and that's because I've been specializing programs that are in a fully linked all LLVM environment. So libc is built as LLVM. System calls are annotated. That's of course one source of assembly blocks that would otherwise be hazardous. That's not too onerous because there's not too many of them, and their semantics are mostly sane enough that I can document them in a way that specialization can continue constructively. The other big source of them is things like SSE operations, byte swap operations, that kind of thing, that tends to bust out into just little assembly bits. LLVM catches me really nicely there. Almost all of those have been raised into nice, friendly LLVM intrinsics, and so their semantics are nice and clear to me. Thank God for that. Then almost the only place where assembly sections hobbled us and did require a bit of manual effort was in the domain of thread local storage. So the implementations of thread local storage were doing fun things where they go look at the bottom of below your stack pointer to go find the thread local storage, the pointers into thread local storage for this thread. That was a bit of fun. That required some manual effort in order to annotate those. and in fact using basically the same annotations as were needed for things like maps and hash maps that are keyed on pointers, in that I basically have to tell the specializer, look, it's an associative container, don't worry too much about the particular implementation of it, just worry about the associative container semantics. But that did present me with some obstacles. Okay, so what have I been actually practically doing with this thing? The purpose right at the beginning, the dream at the beginning of the PhD was try to introduce some staging to big programs. The basic notion here was that there's a bunch of programs we run where intuitively they're repeating stuff from run to run or from request to request that shouldn't be, but it's a pain in the ass to just manually go and stage them. So how about trying to do some automatic staging? So the particular example we got here involves Nginx, the web server, and Xslate, where Xslate, if you're not particularly familiar, is an XML language for transforming XML documents into other XML documents. It's basically sort of style sheet style transformations. The canonical example is usually taking some XML doc that represents some data and turning it into an XHTML doc that sort of prettily illustrates the same data, something like that. But it's a doc-to-doc transform, and it's written out in user-readable XML, well, readable-ish XML, as provided to the web server. So the idea was, every time you request a doc from Nginx that has an Xslate sheet attached to it, then it's going to go, right, what's the Xslate doc? Fetch the Xslate doc, parse that using libxml2 and its partners in crime, parse the doc that we're supposed to be transforming, then run the transform on the doc, and then output. So I thought, right, okay, can we do it so that the parse of the Xslate doc is not done every time? So suppose I've got a big set of data, and there's one Xslate doc that is used lots and lots and lots, and it would be great if we could stage that so that ahead of time we parse the Xslate doc one time, and then for every request that comes in, we use the same pre-parsed, nice, friendly, in-memory version of the Xslate doc to take the particular input and transform that and spit it out. That seems like a good way to save some time. Let's see if we can do that. And so LLPE was the tool used to do this, of course. The idea being that your specialization conditions are, we're going to specialize the Nginx request handler, and we're going to tell you that the request incoming uses this particular Xslate doc, and that's represented by an assumption regarding the function that goes looking for that particular configuration variable. And then at specialization time, it's going to open the Xslate doc, run the libxml2 parser over it, turn that into its in-memory representation, and then return that back to the outer request handler, which is now going to go and use that. So LLPE was able to generate a specialized variant of that, so that instead of actually going and parsing the doc, we're just going to return that in-memory representation, which has been essentially baked into the program, and then just go ahead and use that. And the act of doing so sort of saved like 30% or so of the time that was spent fetching a series of documents that use this sheet, but paid no penalty when you request a document that doesn't use this sheet. And that's because anytime you requested a document which doesn't use the transform, one of our checks fails, we bail out, we use vanilla code, and the server performs as it would have done before. I thought it would actually pay more of a penalty there because we have increased the code size of the server by doing this. We have introduced specialized variants of code, but it turns out that sort of funky cache stuff was not the dominating factor of the performance here, and it turned out to actually perform more or less as it did in the case that we're not exercising the specialized code path. The other side of the coin then, so this was basically making Xslate bigger in the interests of making it faster in certain special cases. The other side of the coin is using this sort of technique to make the same program smaller. So what we did here was specialize the function in Nginx which reads its configuration file, in order to read a particular configuration. So that's a thing you might want to do if you're developing, say, an embedded system. You know the web server config doesn't change from build to build, it's just baked in, it's in a read-only file system. Let's just pare down Nginx, discard the stuff we don't need. Obviously, in the case of Nginx, it's a little bit spurious because it's pleasingly modular to begin with, and we could just go and do that ourselves. But this is a technique we could apply to software which was not written in that way. It didn't assume that that was the case. So basically what we did is we generate the specialized variant, and in this case we tell the specializer, I'm actually certain of my specialization assumptions. And I'm certain of them, of course, because it's an embedded system, I've baked in the config, it's not changing, damn it. So in this case we're certain of our assumptions, and we're able to replace the configuration reader wholesale with one that assumes this particular config. And that means we can then prove a whole bunch of the Nginx code bases unused because we don't exercise the appropriate config parsing code paths that would go and use it. So we end up chopping off, for example, code that relates to HTTPS because that wasn't configured in this particular case. So we've effectively, again, staged the program so that the config read happens ahead of time during specialization, and then the dividends of that are reaped at runtime. All right, so here's the bad side of all this, of course. We're doing some pretty in-depth analysis here. We're sort of going deep into context, and we're always considering the case that sort of memory locations and just direct variables might contain sets of different values and things of that sort, and that's going to impose a pretty big cost. Indeed, at the moment, the cost factor is around 10,000 to 1 relative to just conventional execution of the same program. So in the context of the previous presentation, that's probably about 5 IPS with no prefix. It's better than 5 instructions per second, thank God. I would have never actually finished my PhD. But it does impose a significant slowdown. It's quite probable we could get a lot more out of that. Like, this wasn't being written in order to be lightning fast at the time. It was written in order to make the programs lightning fast. And the specializer itself was of secondary concern. A particular technique which would be really great to use is that of the generating extension. So CMix, which was a previous C partial evaluator, it generated a specializer, which then generated specialized code lightning fast. Really lovely idea. I didn't have the PL chutzpah to attempt that for myself, but it'll be a really nice avenue to pursue to try and sort of raise that cost factor as much as humanly possible. On the plus side, the user assistance required in order to produce the kind of Nginx specializations I was talking about isn't too great. We're talking about sort of 20, 30 or so directives in order to achieve those specializations. One of those I mentioned earlier, which was annotating the thread local storage, and also map containers where the specializer couldn't understand them because they involved pointer ordering. So there I needed to tell it they're associative containers. And also a couple of places where there were loops where they were on an uncertain code path. That meant the specializer wanted to take an approximation about the loop, but actually we needed to look at that in detail in order to get necessary information for the specialization to proceed profitably. So in those cases, I did need to just manually break it and say, look, I appreciate this doesn't look good, have a go anyway, and hey presto, it turns out the loop can actually be proven to terminate. So there's no doubt some good existing work and some good future work for this project to use some smarter heuristics to try and figure out when can we anticipate termination, despite the fact that that we're risking boundless specialization if we go down this way. And to what degree can we do things like use profile data in order to tell us this particular loop, just have a go. It's very likely to terminate within a small number of iterations, so have a go, see if it does, rather than getting scared as soon as you see the potentially boundless construct. And here's the big bad news, of course. We do still absolutely hit the wall when we're confronted with certain situations. So, of course, right through a completely unknown pointer is always hell for this kind of analysis. We know that you might have done anything arbitrarily horrible to memory, And unlike the case where it was another thread maybe doing something horrible to memory, we're not making the optimistic assumption that you haven't done anything critical. We need to assume that you might have done something which is important, and we can't really continue specializing in that direction with any great validity. So it's time to stop there. And the other one, of course, is calls to unknown functions, which of course might be doing anything at all. But by having the fully linked image available to us, it's been typically not a problem. Those have tended to be easily resolved, and I haven't had to manually annotate any of those. And we're trying to salvage as much of that as possible by using these sets of values and things like that, and also by using pointers which are sort of vague, but which are not completely vague. So those are pointers where we know like a set of objects which they point into, and they point somewhere into these objects, but we don't know exactly where they point within them, and that serves just to bound their side effects. So LLVM has turned out to be a really nice place to write this sort of stuff. You get a fully linked image which has rich semantic information attached to it. That's been very, very useful. We get to dodge the shortcomings of the C language because implementation-defined behavior has all been resolved for us. Clang has made some sort of call about what the implementation-defined stuff actually means, and we just take its word for it, so that's been really nice. And of course we get a rich toolbox of primitive manipulations to work with. Some stuff's been a problem. The LLVM's constants get uniqued and kept alive, and that led to huge blow-ups in specializer memory consumption. Needed me to sort of copy and paste the guts of the constant folder out and avoid going into that constant uniquing path whenever we have a bunch of constants that are just momentarily alive. So for example, there was a big MD5 calculation which was getting executed at specialization time, and that generated lots and lots and lots of live constants that actually go away immediately. So that was a bit rubbish. There are things like keeping function passes alive during a module pass. It's an engineering thing. I'm sure that's going to get fixed in due time. And it'd be really great to get IR printout in a structured form, so we can give people like a nice debug output, rather than having to use the simple stuff that actually built the whole module in order to print one instruction. Ultimately though, minor complaints, A++ would develop again. So the current status, 95% feature complete. There's a couple of little missing pieces that are just stuff which I didn't need for the particular stuff I was doing for my thesis, but I'm now trying to sort of move that forwards into an initial release and something which is at least a little bit practical. Just in the process of rationalizing the code a bit, taking the stuff that was sort of written at 2 a.m. In a fog of PhD need done now, and trying to just get that in a sane and readable state and document that a bit more fully. About a month's time or so, I anticipate having completed that process and having a sort of a 1.0 or a 3.6 really. As of this weekend, we got all the proper stuff that you should have if you're trying to make a proper project out of this. So check out LLPE.org. You can find forums and mailing lists, which at the moment is just me, because it is just this weekend. But mail those mailing lists, and thus mail me. And there's bug tracker, feature tracker, all the standard things you'd expect to exist. Get the code off GitHub, play with it, it'll break. Talk to me, I'll tell you how to unbreak it.
Questions?
I wonder what happens if you run Specializer without providing inputs like you did for Nginx. Is there anything it can usefully do, or has all the fruit been picked by the conventional LLVM optimizer?
If you gave it nothing at all, then the only things I would expect it to really get out for you would be things where a function actually is just completely constant, but the conventional optimizers got scared because there were loops with millions of iterations, or that we did need to do, the compile time would have been long, and hence the conventional optimizers were scared away. That's really the only case where I'd expect to see a lot out of that, but that is, of course, that would be perhaps a good usage if you were wanting to avoid having to manually hack that sort of stuff.
Or?
maybe one question getting back to your statement about exceptions that you can specialize across a flow. So I was wondering, so I mean the reason why the flow has all this machinery to read revolve CFI and so forth is really just to get the call chain because it doesn't know where it's been called from, right?
Yeah.
But if I understood you correctly, if you specialize, basically you specialize in context, at this point shouldn't you know your call chain already? So all that stuff is...
I do know the call chain, but what I don't know is where you want to catch it. Because I can see landing pads, but I can't understand whether those landing pads correspond to the language-specific type info that you were throwing. Or perhaps I can. To my knowledge, I don't know that. If it is actually possible with pure IR to fold that, then great. I would love to hear from you. But I don't personally think I have enough information without parsing some of that like really hairy guts of libcxxrt to find out how it's encoding that and how it's decoding that at the landing pad.
Okay, one short question. Nobody? Then thank you, Chris.